Hello everyone, this is Babitha, working as Assistant Professor in the Department of ECE at Institute of Aeronautical Engineering. In this session, I am going to explain about Class B power amplifier and Class AB power amplifier and Class C power amplifiers. So while coming to the contents, before going to the classification of power amplifier, just I'll revise few points related to the power amplifier. And next about Class B, Class AB and Class C power amplifiers. What are the construction and operating principles of all the three power amplifiers and advantages, disadvantages and applications of different power amplifiers. So while coming to the power amplifier, till now in the previous sessions we have seen the single stage amplifiers as well as multi-stage amplifiers. Those are used to provide the different voltage levels as well as current levels. But in order to run some practical applications, the voltages as well as currents provided by the single and multi-stage amplifiers are not sufficient. So in order to run such type of applications, we need to provide the power signal as the input. So in order to generate the power signal, we are moving for the power amplifiers. Anyway, to run any large signal application, we require both these small signal amplifiers as well as large signal amplifiers. Those are nothing but voltage or current amplifiers and power amplifiers. So here, for example, I am taking the practical application of loudspeaker. So to run this particular loudspeaker, we are giving the signal from the microphone. The input signal we are providing from the microphone here. So the signal coming from this microphone is with less amplitude. So in order to amplify that particular signal, I'm using the two stages of voltage amplifier here. So the first stage of voltage amplifier will amplify this particular signal and it will give the output as some V0 or V01. So that same output of this first voltage amplifier is giving back to the input of the next voltage amplifier like input. So the output of this voltage amplifier, again we are taking here it as V0. So from the first amplifier, we are getting the amplified version of the applied input signal. But again, that amplified signal, again we are giving back to the second voltage amplifier, so that still more the amplitude or strength of the signal will increase here. Then we are giving that to the input of the power amplifier. So generally power amplifier will run the signal with 1 watt or more power. Then only we can call it as the power amplifier. So we are providing such type of signal here so that it will provide the large signal as the input for the loudspeaker. Then only the loudspeaker can able to accept that particular signal and it will provide the proper high sound as the output. So in this particular part, we are going to use the different types of power amplifiers. So among these all the power amplifiers, in the last session we have seen the Class A power amplifier. That Class A power amplifier will conduct for total 360 degrees of the applied input signal. So it is going to utilize the total full applied input signal for converting into high power signal. But here we are getting the problem of efficiency in the case of Class A power amplifier. Just we are reaching the 25% of efficiency with the Class A power amplifier. It is very less. So that's why in order to improve this efficiency factor, we are moving for the different another types of Class B, Class AB and Class C power amplifiers. So before going to that, in the power amplifiers, we are having two types, small signal amplifiers and large signal amplifiers. So if you take the small signal amplifiers, which are handling with the very small input AC signals. So it will take the input as very small signal, that is almost some microvolts to few millivolts signal range. So it will accept that particular range of signals and it will amplify that particular signals. So the voltage amplifiers as well as current amplifiers come into this particular small signal amplifiers, and these will operate over the linear portion of the output characteristics, so that we can say these are the linear amplifiers. And In the small signal amplifiers, if we take the amplifier parameters, those are current gain, voltage gain, input impedance as well as output impedance do not change with the signal conditions or signal changes, so that it will provide the amplification of the applied input signal with some little distortion. Actually, if we take the ideal condition without distortion, it will provide the amplified signal, but in the practical case, we may not get without distorting the signal. So that's why with a little distortion at the output, we can expect from the small signal amplifiers. And next category is the large signal amplifiers. So any particular amplifier handling with high range of signals, that is large input signal as the input, and it amplifies that particular large input signal, so that we can call it as the large signal amplifiers. So what are the power amplifiers we are using? Those comes into this large signal amplifiers. So these large signal amplifiers are designed in such a way that in order to provide the large amount of AC power output, so that we can able to run different high power applications. For example, we can say here it as speaker. And in the case of large signal amplifiers or else power amplifiers, those are specifically useful to provide high efficiency as well as impedance matching. Wherever we require the high efficiency as well as impedance matching between the stages, in that case we can able to utilize this large signal amplifiers. So while coming to the classifications, the second classification is the class B power amplifier. In the case of class A amplifier, I have already mentioned that the class A amplifier is utilizing the total 360 degrees of the applied input signal. But in the case of class B power amplifier, it is going to utilize only half of the applied AC input signal. That is nothing but till 180 degrees only the amplifier is going to accept the signal. So we have to design the power amplifier in such a way that it should take only half of the applied input signal. So to get the half of the input signal, we have to keep the operating point at the cutoff region of the transistor. So in the transistor, we are having three regions: cutoff region, saturation region, and active region. If we keep the Q point in the active region, we will get the full amplification of the signal and we will get the signal without distortion. And if you keep it in the saturation region, there is a clipping in the positive half cycle of the input signal. And similarly, if we keep the operating point across the cutoff region, we can able to reduce the total negative half cycle of the applied input signal. So because of that reason, we are maintaining the operating point at the cutoff region in the case of class AB power amplifier. So that's why I am indicating the Q point or operating point in the cutoff region. So this one is the cutoff region and this is active region and this one is the saturation region. So to get the operating point, first of all, we have to take the output characteristics of that particular amplifier. So in this case, we are considering the common emitter configuration. So in the common emitter configuration, output voltage is VCE and the output current is IC. So if we draw the characteristics between the VCE versus IC, we can able to get the different output waveforms. While drawing these particular characteristics, we have to maintain the input voltage as some constant. The input current as some constant value. So if you maintain a different constant input currents and if you vary the VCE voltage, then we will get the corresponding IC current in the case of common emitter configuration. So after getting the output characteristics, we have to draw the load line in order to get the proper operating point. So to draw the DC load line, we have to get the expression for the output voltage as well as output current equation from the circuit. Then if you substitute VCE equal to 0, we will get the IC value. And if you substitute VCE IC equal to 0, we will get VC value. See, if we keep the 2 points on the corresponding axis and if we draw the line in this way, then we can get the load line here. Okay, this one we are calling it as the load line. And after drawing the load line, wherever we need to choose the operating point, it depends upon how much voltage as well as current level we are setting in the amplifier. So in this particular case, we want to run the amplifier in the cutoff region. So that's why we are keeping the Q point in the cutoff region, so that it can get the signal only this much and this remaining portion is flipped off or 0. So that's why in the class B power amplifier, across the output, we will get this signal only half of the applied input signal, this much. So the total negative cycle is 0. Okay, so in the class B power amplifier, we have to bias the transistor in such a way that the operating point should be in the cutoff region I have mentioned, and whenever we are not applying any signal to the amplifier, at that time we should not get any collector current from the circuit. Okay, and the operating point is selected in the cutoff voltage. So when the signal is applied, only the positive half cycle is amplified at the output. And here the operating point or Q point is located at the x-axis only, that is on the VCE axis. So due to this, collector current flows only for a half cycle, for a full cycle of the input signal. So hence the total signal is distorted here. So among the total 360 degrees, it is going to utilize only 180 degrees. So that's why there is so much of distortion will occur across the output. So to get full cycle across the load, total 360 degrees across the load, we have to use 2 transistors in the class B power amplifier. So these 2 transistors we have to conduct in alternate manner. That is nothing but for positive half cycle, one transistor is in on state, one more is in off state. Similarly, for the negative half cycle, one transistor is in on state and one more transistor is in off state, so that we can able to utilize total applied 360 degrees input signal and we can able to reduce the distortion across the load here. And here we are telling that 2 transistors are going to utilize in the case of class B power amplifier. So depends upon which type of transistors we are going to use and which type of connections we are going to made in the circuit. These class B power amplifiers are divided into 2 types. In that, first one is, suppose if we take 2 transistors are of similar type, that is both are NPN transistors or PNP transistors, so that circuit is called as push-pull class B power amplifier. Or else if we take the 2 transistors are different, one is PNP transistor and one more is NPN transistor, so that we can call it as complementary symmetry push-pull class B power amplifier. So the 2 classifications are push-pull class B amplifier and complementary symmetry push-pull class B power amplifier. So now we are going to see these both the types of power amplifiers. So in that, first of all, I am taking the first classification, that is push-pull class B amplifier. So in order to design this particular circuit, we require here 2 center tapped transformers. One is at input side and one more is at output side, and 2 identical transistors, that may be our NPN or PNP transistors, and we require the DC power supply in order to run the transistors or in the remaining elements in the circuit. So across the input side, we are taking 1 center tapped transformer here. Okay, and the secondary winding of the center tapped transformer is divided into 2 halves. That is the basic difference between the normal transformer and center tapped transformer. So in the case of normal transformer, the turns ratio is N1:N2. N2, but in this case N1 is to N1 by 2 will be there in the center tap transformer, so that the total applied signal is divided into two halves. One is to the first half of secondary winding and second to the second half of secondary winding. Okay. And the two ends of the secondary winding of center tap transformer is connected to the bases of two identical transistors here. These Q1 and Q2 both are NPN transistors here. Okay, and emitters of these two are tied together, and that is connected to again the output center tap transformer. And the output of the circuit we are taking generally across the collector terminal of the transistor. Why? Because these transistors again we are taking in the common emitter configuration. In the common emitter configuration, always the output we will take across the collector terminal, so that the collector current IC as the output signal we will take, and VC as the output voltage we will take across the both the transistors. So the collector terminals of both the transistors are connected to the primary winding of the output center tap transformer. Okay, so according to that, due to the mutual inductance concept, the signal will pass to the secondary of the transformer, and so it is actually connected to the secondary winding already, so it is transferred to the primary winding, and through this primary winding it is connected to the load resistance RL. So the overall output voltage we will measure across the load resistance RL. So this is the construction of the push-pull class B power amplifier. And while coming to the operation of this push-pull class B amplifier, we will apply the input signal, AC input signal, to the primary winding of the first center tap transformer, and this applied AC signal is divided into two halves, VAC by 2 here and VAC by 2 here. Or else we can take, if we take it as maximum voltage VM, we will get it as VM by 2 here as well as VM by 2. Here where VM is nothing but maximum amplitude of applied input signal. So this half, that is nothing but when you are giving the signal, it is going to divide into two halves. One half is for base of the Q1 transistor and one more half is connected to the base of the other transistor. Here the voltage is divided into two halves, but the polarity of that signals are in opposite phase here. That is nothing but if the positive half cycle is connected to the base of first transistor, so that the negative half cycle is connected to the base of the second transistor. So that for the positive half cycle, we are providing the positive voltage to the base of the Q1 transistor, so that Q1 is going to conduct now. So once the Q1 is going to conduct means there is a flow of collector current IC1 in the first transistor, and that is connected to the secondary winding of the output center tap transformer. And similarly in this case, the second half, that is negative half cycle, is connected to the base of the Q2. So once the secondary half is connected to the base of the Q2 means this transistor is in off state now. This is in on state, this is in off state. So once this transistor is in off state means there is no flow of collector current in this, so that only the current IC1 is flowing in the circuit, and due to the mutual inductance that is transferred to the primary winding of the transformer, so that across the load resistance RL we can measure the current as IC1. Okay, and similarly if I take my second half cycle, negative half cycle, keep negative half cycle of this applied input signal. So this negative half cycle directly applied to the base of the Q1 here, and I have already mentioned when you are providing the voltage, it is divided into two halves and with opposite polarity here. So it is in the negative half cycle means obviously in the second transistor, for the second transistor it will going as positive half cycle because of opposite polarity. So once for the first transistor we are providing the negative voltage means it will goes from on to off state. And similarly, while coming to the second transistor, once the voltage is changing from negative to positive, so that this will change from off to on state. So in this case, the transistor Q1 is in off state, so there is no flow of collector current IC1 in the circuit. But the transistor Q2 is in the on state, so that there is a flow of collector current IC2 in the circuit, and that is connected to the secondary winding of the center taper transformer, and due to the mutual inductance that is transferred to the primary winding, and from there we can measure the output voltage across the load resistance RL. In this case we will get it as IC2. So both the currents are flowing in the same direction. If you observe in the circuit, it is also in this direction it is flowing, and it is also flowing in this direction. Okay, so that's why across the load the total current is equal to IC1 plus IC2 currents we will take here. And in order to find the efficiency of this class B power amplifier, we have to calculate the DC power input as well as AC power, how much we are getting from the circuit. So in order to calculate DC power input, we have to take the output across the each and every transistor. That is nothing but each transistor output we are getting in the form of half wave rectification waveform, so that Im is the peak value of the half wave rectifier output. So the DC or average value we will getting here it as Im by pi due to the half wave rectifier waveform. So here the two currents drawn by the two transistor from the DC supply are in the same direction. I have already mentioned. So once they are flowing in the same direction means we have to take the average current is the sum of individual current which are flowing in the transistors. So that's why IDC or average current we are taking here it as Im by pi plus Im by pi. So this Im by pi is due to the transistor Q1 and this one is due to the transistor Q2. So the total DC or average current we are getting from the circuit is 2 Im by pi. But the total DC power input from the circuit is given by PDC, that is the multiplication of DC voltage as well as DC current. So DC voltage is nothing but we don't have any other voltages here. The supply voltage itself the DC voltage here. So that's why I am writing in the place of VDC directly as VCC, and IDC is the DC current coming from the circuit. Okay, and PDC is equal to, in the place of IDC, I am substituting here it as 2 Im by pi. So it will become 2 VCC into Im by pi. This is the DC power from the circuit. And similarly, we need to calculate the AC power output. So the AC power output we can express in terms of RMS voltage as well as RMS current. So that's why PAC is equal to VRMS into IRMS. And we can also write it as IRMS square into RL dash. That is nothing but we are writing in terms of IR. So that is nothing but VRMS is equal to IRMS into RL. So if we substitute here, we will getting here it as I square RMS into RL dash. And if you want to write in terms of voltages means, we have to take it as IRMS value, that is VRMS by RL. So in that case, we will get it as VRMS square by RL dash. Why? Because already one VRMS is present in the equation. So if you write in the peak to peak values, we will be getting here it as PAC equal to VM into Im by 2. And we are substituting the value of Vm, that is Im square RL dash by 2. So Vm square by 2 RL dash, this total values. So the total AC power drawn from the circuit is Vm square by 2 RL dash. So in the efficiency expression, that is the ratio of DC power to the AC power, in that we need to substitute both the DC power as well as AC power values, so that we can able to find the efficiency of the class B power amplifier. So that's why POAC by PN DC, that is output power to the input power. Here output power is in terms of AC power, input power is in terms of DC power. So that's why PAC by PDC we are taking. So now substitute the values of this PAC as well as PDC here. PAC is PM Im by 2 and PDC is 2 VCC into Im by pi. Okay. So if we take this pi by 2 term into the numerator, we will be getting here it as pi by 2 here. So that is nothing but 2 into 2 is 4, pi by 4 into Vm by VCC. This Im will get cancelled. So here Vm value is VCC, the how much applied voltage we are taking or DC voltage we are applying. To get the maximum efficiency, we have to take it as maximum value, that is VCC. So that's why in the place of Vm, I am substituting here it as VCC. If we keep in that way, we will get these two terms will get cancelled, and pi by 4 into 100, we will get it as 78.5%. So the overall efficiency of class B power amplifier is 78.5%. If we compare it with the class A power amplifier, it was 25% only. So almost 53.5% of efficiency is increased in the case of class B power amplifier because of utilizing 2 transistors for the conduction alternating. And while coming to the advantages of class B power amplifier, here the first main advantage is the efficiency is very high compared to the class A operation. Just now I have mentioned almost 53% is increased compared to the class A power amplifier. And when we are not applying any input signal, there is no power dissipation in the circuit. Why? Because it is not providing any output when we are not applying the input. So that's why power dissipation is also 0. And even harmonics which are coming from the signal are also get cancelling here. This reduces the overall harmonic distortion in the circuit. And the DC currents are flowing in the opposite direction through the primary winding of the transformer. So there is no chance of DC saturation of the core or winding here. So ripples present in the supply voltage are eliminating due to the alternate conduction of the transistors. And because of utilizing the 2 transistors, we can able to provide the best impedance matching between the source and load in the circuit. So these all are the advantages of the class B power amplifier. And while coming to the disadvantages, actually center tap transformers are we are using in order to construct the circuit. These are very bulky and costlier. And frequency response is also very poor for this class B power amplifier. Why? Because we are not utilizing the total applied input signal, only half input signal we are utilizing, so that the power or response is also very less here. And next type of class B power amplifier is the complementary symmetry amplifier. So this is the circuit for the complementary symmetry push-pull amplifier. So what is the basic difference between the push-pull class B amplifier and this one here? Means we are not using any center tap transformers here. In this particular case, we are not using any center tap transformers. Only one single transformer we are using in order to measure the output here. Okay, and one more thing here is, instead of using 2 identical transistors, we are using 2 different transistors, NPN and PNP transistors. So these 2 are the basic differences between the class B and complementary class B power amplifiers. So to construct this particular complementary symmetry amplifier, we require two transistors. One is NPN transistor and one is PNP transistor, and one normal transformer without any center tapping, and as well as the supplied signal as the input, and also the biasing network in order to provide the proper biasing for the two transistors. So this is the RB resistance in order to provide the biasing for both the transistors and for the primary winding. Okay, so here in this case, during the positive half cycle of the input signal, so the transistor T1 will conduct. So this signal, we are providing sinusoidal signal with the maximum amplitude Vm, it is varying with respect to T. This is the input signal we are applying for the transistors, and this RB resistance is used to provide the biasing and in order to maintain the proper operating point and in order to provide the proper stabilization for the transistor. So that is the basic requirement of the RB resistance in the circuit. Okay, so for the positive half cycle, if we are applying the positive half cycle, means here positive, and the same signal is also appearing across the transistor T2 also. So for the positive half cycle, T1 is going to conduct. Why? Because it is the NPN transistor. So it is going to conduct so that current IC1 will flow in this particular transistor. But in this particular case, the same positive half cycle we are applying for the PNP transistor, so that it will be in the off condition. It is in the on state, it is in the off state, so there is no collector current, that is 0 here. So the current which is flowing in the collector of this one is connected to the primary of the transformer, and due to the mutual inductance concept, that is appear across the secondary of the transformer and across the load resistance RL, we will measure the output voltage V0. Okay, and similarly, if we take the negative half cycle, as the input signal, so that we are going to provide the negative half cycle in both the cases or both the transistors. So when you apply the negative voltage to both the transistors, the transistor T1 will become on to off state now. Why? Because we are providing the reverse polarity of the signal here. And similarly, while coming to the PNP transistor, it will change from off to on state. So once this transistor is in off state, means so the IC1 current is 0 here. So this one is conducting, means IC2 current is present in the transistor or increasing in the circuit. So due to this, the IC2 current is connected to the primary winding of the transformer, and due to the mutual inductance that is appearing across the secondary winding and across the load resistance, we can measure the output voltage. So that is nothing but here we are going to utilize the total full cycle, one half cycle for conduction of the one transistor and one more half cycle in order to conduction of the second half cycle. So these transistors are conducting in alternately in order to provide the output current as well as voltage. So this is the basic operation of the complementary symmetry amplifier. So while coming to the advantages of this complementary complementary push-pull amplifier, here we doesn't require any center tap or transformer, so that the cost will be reduces and size of the circuit will reduces and weight of the circuit is also reduces. Here we are taking equal and opposite input signal voltages, not required here. In the previous case, class B amplifier, we are using equal and opposite polarity input signals in order to conduct both the transistors. But here in this case, it doesn't require in that way. In the single applied input signal, we are utilizing half cycle for the first transistor and remaining half cycle for the second transistor. And while coming to the disadvantage, it is very difficult to get pair of transistors NPN or PNP that have similar characteristics. That is nothing but we are using one NPN transistor and one PNP transistor, but the characteristics should be same here. Then only we can able to utilize in this circuit. So in order to get same characteristic or similarities of the transistor is very difficult. And we require both the positive and negative supply voltages in order to provide for both the PNP and NPN transistors. And next classification is class AB power amplifier. So here till now we have seen the class A power amplifier as well as class B power amplifier. So in both the cases we are getting some limitations. In the case of class A power amplifier, efficiency is less, but in the case of class B power amplifier it is costly, heavier, and also we are getting the distortion in the output signal. So if we use this class A as well as class B as combinedly to get the advantages of both the amplifiers and without taking into their inefficiencies or disadvantages into consideration. So, but we can able to combine the two power amplifiers or class A and class B power amplifiers, but before going to that, we will get some distortion in the class B power amplifier. That one is the crossover distortion. So what is mean by this crossover distortion? In the case of class B push-pull configuration, we are using two similar transistors get into conduction one after the other, but output is a combination of both the transistors. But whenever the signal is changing from one state to another state, from positive position to negative position or from on state to off state, at that time one transistor is going from on state to off state and other one is going from off state to on state. And also at zero voltage input also it is providing some output in the form of distortion. So for a transistor, in order to get into conduction, we have to provide the base to emitter voltage as 0.7 ohms. So the time taken for the transistor to change from on to off state and from off to on state is called transition period. So because of this transition period present in the class B amplifier, we are getting this crossover distortion. In this particular circuit, one is conducting one time and one more is conducting one time. So when the Q1 is changing from on to off state and when it is changing from off to on state, it will take some time. When it is changing from one state to another state, it is taking some time. So because of the time taken for the transistors, we are getting the crossover distortion. So how we can able to see this crossover distortion? I am showing here. This is the applied input voltage with the positive and negative half cycles with the maximum and the minimum amplitude of the signals. And across the output of the transistor Q1. Okay, because the output of the transistor Q1 is nothing but whenever the transistor Q1 is in the on state, we will get the collector current IC1. So that we will get the collector current IC1 in this way. For the positive half cycle, we will get the output, and for the negative half cycle, it is 0. Similarly, it will repeat for all the cycles. And similarly, during the negative half cycle, the transistor Q2 is going to conduct. Okay, that's why for the positive half cycle, it is 0. For the negative half cycle, it is providing the output. But if you observe here, at that whenever the transistor is changing from one state to another state, at that instant only we are not getting the collector current here. There is some gap here, that is the time period or transition period. So because of the time period or transition period, in the output voltage also we are getting the gaps here. In this particular gaps there is no voltage. The voltage is 0 here. Even though we are getting the output for both the positive cycle as well as in the negative cycle, but when we are changing the status of the transistors, in that time we are not getting the output. In all these cases, the output voltage is 0. So this one we are calling it as the crossover distortion. So the same thing again I have mentioned here, this crossover distortion is occurring in the circuit. Okay, suppose when you are providing the input voltage as 0, so the transition period of switching of the transistor from one state to the another state, which is affecting the transistor in the form of crossover distortion. So this one we are also called as flat spot or dead band on the output wavesheet. Okay, so this crossover distortion, because of this, overall peak to peak value of the output voltage is decreasing here. Okay, why? Because there is some gap in the waveforms. Because of that reason, overall peak to peak voltage value is reducing. So once the overall peak to peak voltage value is reducing, means the output power will also reduces. So from the crossover, if the crossover distortion is less, means, so in order to maintain the less crossover distortion, we have to provide the large signal as the input for the amplifier. And if you provide the small signal amplifier, so that crossover distortion will be more. So the crossover distortion can be eliminated if the conduction period of the transistor is more than 1/2 cycle. In the previous case, we are taking half cycles, positive half cycle ones and negative half cycle one. But because of this changing from one state to another state only, we are getting the crossover distortion problem. But if you maintain the input voltage range as more than half cycle, suppose till here, or in this case from here, if you maintain more than 1/2 cycle, so that we can able to reduce the crossover distortion. Why? Because if you maintain the input waveform in this way, there is no chance of stop or getting the transistor into off condition, or else once it is going into the off condition, before that only second transistor is going into on state, so that every time one transistor is in the on state if you maintain the input signal in this way. So in the class AB amplifier, we are going to implement this one. So here class AB is the combination of both class A amplifier as well as class B amplifier. So here in the class AB amplifier, the problem of class A amplifier, that is low efficiency problem, is eliminated, and also the crossover distortion of the class B amplifier is also eliminated. Both the efficiency as well as crossover distortion problems are eliminated in the case of class AB power amplifier. So the crossover distortion is occurred whenever both the transistors are off at the same instant during the transition period. So in order to eliminate this, the condition is we are choosing for more than 1/2 cycle we have to give to the transistor. So the other transistor gets into conduction before the operating transistor is switches to cutoff state. So this is achieved only by using the class AB configuration that is shown in this particular circuit. So what is the basic difference between the class B push-pull amplifier and this one? Means we are including the diodes in order to maintain the more than 1/2 of the applied input signal. So in this case, we are providing the input signal so that according to the applied input signal, this transistor NPN for the positive half cycle, NPN transistor will conduct, and for the negative half cycle, the transistor PNP will conduct here. So according to that, we will get the output voltage V0, and already we are chosen the condition that always here the first half cycle is more than 1/2 cycle, and similarly when we are taking the second half cycle, it should be also more than 1/2 cycle, so that whenever we are providing this particular waveform, this T1 is going to conduct, and whenever we are providing this one, T2 will going to conduct. But whenever we are providing this particular wave to T2 transistor, before turning off this T1 transistor only, T2 will going into conduction state. So always any one of the transistor is in on state, so that we can eliminate the crossover distortion problem here. So here class AB is the good compromise between the class A and class B here, and we will get the efficiency also between 50 to 60 range in the case of class B amplifier. So whatever the amplifiers we discussed, class A, class B and class AB are linear amplifiers here, because the output signal amplitude and phase are linearly related with the applied input signal amplitude and phase here. So in the class AB amplifier, the conduction angle is between 180 degrees to 360 degrees. Why? Because we need to maintain more than one half of the input signal. So that's why we are giving the input signal, this one, and we are making the Q point here. That is nothing but it is taking this particular waveform as well as this one as the input, and we will get the corresponding output here. This shaded one is the output we got from the class AB power amplifier. And while coming to the advantages of this class AB power amplifier, it is having linear behavior and it is simple circuit. Why? Because we are not using any transformers to design this circuit. Only diodes and transistors we are going to utilize to design this particular circuit, and the distortion of this one is very less, almost 0.1% is here, and the sound quality of this class AB power amplifier is very good in quality. We will get very high sound. So these are the advantages. So we achieved the efficiency as well as less distortion by using the class AB amplifier. And while coming to the disadvantages, we are having the much power dissipation here. So in order to reduce this, we have to utilize the heat sinks in the circuit, and efficiency is less than 50%. Theoretically, we estimated here it as 70%, but in the practical case, we can reach up to 50 to 60 range only. So that's why I mentioned here it as 50% only. And the applications is, here we can use it as hi-fi receivers. That is nothing but wherever we require the high sound devices or high fidelity devices, we can utilize this class AB power amplifiers. And in order to design this one, we require toroidal transformer. Across the output of the circuit, we are using one transformer to measure the output voltage. So in that case, we require the toroidal transformer. So this toroidal transformer is different with the normal transformer. So it is the power transformer. It is made up of with a toroidal core on which primary and secondary windings. And the last classification of power amplifier is the class C power amplifier. So here in the class C amplifier, we are taking the input signal as less than the half of the input signal. Okay, it is going to utilize less than half of the applied input signal for the conduction. That is nothing but almost 80 to 120 degrees signal only it is going to utilize for amplification. So because of this reduced conduction angle in the circuit, it improves the efficiency, but because of this, there is a lot of distortion in the circuit. The efficiency is increasing, but distortion is also increasing along with the efficiency here. But theoretically, it may provide 90% of the efficiency here. So due to this large distortion problem, the class C configuration mostly we will not prefer in the audio applications. So this is the circuit for the class C amplifier. So this RB resistance is used to provide the biasing for the transistor Q1. Okay, and this L1C1 is used as the tank circuit for the tuning purpose in order to get the desired frequency range. And here this RB resistance is used to provide the biasing in such a way that it should conduct less than half cycle of the input signal. Okay. So here the transistor is used to produce a series of current pulses according to the input and make it flow through the resonant circuit here. So the values of this L1 and C1 are selected in such a way that the frequency of it should oscillate with the applied input frequency signal. Okay, so here since this resonant circuit oscillates in one frequency, generally for the carrier frequency, for all other frequencies it will be attenuated. Okay, and the harmonics as well as noise in the output signal can be eliminated using additional filters across the output here. And a coupling transformer can be also used for the transferring of the power to the load here. So this is the input-output signals in the case of Class C power amplifier. So the input signal we are providing only this particular range here, okay, less than half cycle. So in the output also we are getting the output signal this much only, less than half cycle. So mostly Class C power amplifiers will utilize in the RF oscillators or RF amplifier circuits. So while coming to the advantages of Class C power amplifier, it is providing highest efficiency compared to remaining all the power amplifiers, and it will be useful in the RF applications, and it is very less size for the given power output. And while coming to the disadvantages of Class C power amplifier, linearity is very less. The remaining all the amplifiers is providing linear operation, Class A, Class B and Class AB, but this is non-linear, and it is not suitable for all the audio applications, and it is creating so much interference in the circuit, and it is difficult to obtain ideal inductors and coupling transformers in order to design this type of circuits, and reduced dynamic range here. So output dynamic range is nothing but output dynamic range is the range, it is given in dB, that is the smallest and largest usable output levels that we will measure between the smallest and largest output levels. So the lowest useful level is limited by the output noise, and the largest is limited mostly by the distortion here. So the ratio of these two is quoted as amplifier dynamic range. So the overall amplifier dynamic range is reducing due to the noise as well as distortion from the circuit. Well, coming to the applications of Class C power amplifier, we can utilize for RF oscillators in order to generate the waveforms, and in the RF amplifiers in order to amplify the signals, and in the frequency modulation transmitters in order to send the signals, and in the booster amplifiers in order to improve the efficiency as well as amplification, and in the frequency repeater circuits, and in the tuned amplifiers we can able to utilize this Class C power amplifier. So in this session we discussed about Class B, Class AB and Class C power amplifiers, in that the construction, operating principle and the advantages, disadvantages and applications of all the three power amplifiers we have discussed. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.